Hey, what's up, guys? So previously we talked about the property called affine local. So this video, let's just make a choose a simple case and give you one example of so-called give you one example of affine local. Okay. So recall that right. So when we say uh affine local, it said this need to satisfy property. So basically, the first property is that if spec A or has property P, and the distinguished open set have, right? So that D of like F I has property P. Okay, the second one is that if you right, if your A is F1, F2 of Fn, and each of D of Fi has property P, then then spec A has property P. Okay, so this is the idea called affine local. Okay, and if you have this affine local, then as we previously said, you can derive results called affine communication theorem. Okay, so this theorem is not easy to prove. You need to use a weird intersection lemma that proved by Cal or in the textbook. Then you can prove this affine communication theorem. Okay, so this video, let's provide a very simple case. So who is a affine local? Who is a affine local? Well, affine local basically say that if the local one is true, if the global one is true, then every local one is true. If all the local one is true, then if all the local one are true, then global one is true. Okay, so let's play around with simple case. So this video just talk about reduce. Okay, so reduce is a special one, right? So basically I want to say that reduce is a final one. Right, so basically this is just the property of ring theory. Okay, so let's play around with it. And so basically we first need to show that if A is reduced, non-important, we want to prove that each localization is reduced. Okay, so this proof is interesting. So you can think about it, how to prove it, but let's try to prove. So let's prove suppose not. Right? So suppose not. So this ring is non-important. We want to prove that the localization, the ring of localization has no input. So let's say we choose R of Fn, right? AFn, and let's say power m to be 0. Okay, cosine m. But R divided by Fn is non-zero. Okay, so remember it's non-zero in AF. Okay. Okay. So now so this tell me that R to the m f and m is 0. So this tells me that there is this f maybe to some power g where R to the n is 0. Okay. It is some g. Okay. And this tell me that 0 in A, right? So you remember you need to somehow like remember to write this, otherwise that you're getting stuck, right? You know that because you're translating into these two different rings. Okay, so now what is going on? So now from here we get fg to the r to the m, right? Is 0, right? Because you can write this fg to r to n to be f however r to n, right? So you can write this fgm r to n, right? Because you in A. Okay, but A is reduced, right? So this tells me that fg to the r is 0, right? Then r divided by fn is 0, right? Contradiction. Because fg r equals 0 in AF. In A will translate into r divided by anything is 0 in AF. Okay, then this contradiction that I say these guys important. Okay. Okay, so this one is simple, and the second one is also interesting, right? So you should play around with it. So second one is that suppose A is f1, f2, fn, and then we want to say that if each fi is reduced, and then A is reduced. Okay, this guy is interesting because okay, so let's prove. So how do I play around with it? So so what should we do? Okay, so we still prove. So this is the same as we try to prove that if A is not reduced, then there exists I, right, such that AFI is not reduced. Okay, so let's prove this sentence. Okay, so suppose that we prove by condition. Okay, suppose that let's say we took x to the n is 0 and the x is non-zero. A, so x is important, and then we just pass into each f, right? So we just ask x divided by 1 in considering AFI. Okay, but this means that by definition, right, you know that x1 to the n is 0 in there, 1 to the n, sorry, 1 to the n is 0 in AFI. Okay, so this means that there is a fi to the some power mi such that xn is 0. Okay, but okay, let's see. So okay, so our goal is to suppose now. Suppose now means that there is I such that for every I such that the AFI is reduced, right? So suppose now. So this means that if I get this means that if I get x divided by 1 and to the 0 in AFI, since all I, right, since all I AFI are reduced, so I want to prove by contradiction, right? So I need to assume that for every I AFI reduced. So this tells me that x and this tells me that this will implies that x divided by 1 is 0, right? In AFI because AFI is still reduced, but this just tell me that this is the same way we get fi x is 0, okay, for every I. But as we say is that if you write this, then this is well the same as if you write f1 to the m1, f2 to the m2, up to fn to mn. This is the technique that we prove that the spectrum of the ring is indeed the structure. Affine scheme is really a local ring space. So if you have this, then basically you are saying that when there's a coefficient, right, one called there's a coefficient gi fi mi such I from 1 to n produce 1, right? So if this is true, then you times x, then you get a gi fi mi from 1 to nx, right? You get 0, right? Because all these guys are 0. Okay, x is 0, right? Contradiction, because I assume that x is non-zero, so x is unimportant, but you prove that x is 0. Okay, so that means that our result is our assumption is our contradiction proof is okay. So we prove that there is this I such that fi is not. Okay, so this is just very simple proof that just give you one example that exactly is a fine local, so you can use. So if you list, then you prove that you can apply the affine communication theorem on the reduce. Okay, so see you guys. Be sure to subscribe to my channel.